Hey everybody, today I'm going to go over the review problems for Econ 140's midterm number 1. These are the practice problems looking at some of the stuff you might see on the midterm and a refresher of what you want to expect and be comfortable with. So let's go ahead and open this up. So there's a couple of problems that are multiple choice, and then there's an interpretation problem. The first problem asks, taking the log of a set of data means A, the coefficients can be interpreted as constants, B, the coefficients can no longer be interpreted, C, coefficients can be interpreted as elasticities, or D, coefficients can be interpreted over time. The answer is C, they can be interpreted as elasticities. And there aren't going to be a lot of questions about this. But what you want to remember is that what we're talking about here is going through and taking the log of both sides of the equation. So if I've got my, sorry, I'm just going to try and see if I can see the camera here so I can make sure you guys can see this. There we go. If I've got my regression equation where I've got y equals alpha plus beta x plus e, what we're talking about is taking the log, or commonly just the natural log of y and the natural log of x. And that's just a simple data transformation. But what that does is it means that now we're looking at the percent change in x and the percent change in y. And when we're looking at an elasticity, we're looking at the effect of a percent change in one variable on another. So for example, if we wanted to look at the price elasticity of demand, what we are looking at is the percent change in quantity demanded divided by the percent change in price. So that's what an elasticity is definitionally. And so when we're looking at the percent change of x on a percent change in y, where you can interpret those coefficients, that beta is going to be the elasticity of whatever x and y are: income elasticity, price elasticity of demand, price elasticity of supply. It's not something we're going to deal with a lot, but it's definitely really useful to know and remember. So the next part gives a regression table showing the regression of sale price on lot size, bedrooms, and bathrooms. And I'm going to switch it to the screen so you can see the results I'm talking about. So give me just 1 second here. Here we have the table in the assignment, and we've got the regression of sale price on lot size, bedrooms, and bathrooms. We have our estimated coefficients, our beta hats. We have our constant, which is our alpha hat right here. And then we have our standard errors, our t-statistics, our p-values for those t-stats, our 95% confidence interval. And then up here we have our ANOVA table, which gives us our sums of squares, our total sum of squares, our sum of squared residuals, and our regression sum of squares. We've got the number of observations and our degrees of freedom. We also have our R squared and, oops, don't move it, and then our F-stat and our p-value for our R squared. So the first question asks you to conduct a null hypothesis, conduct a test of the null hypothesis that beta is equal to 0 and explain how you conducted the test and what it means. The next asks you to interpret the coefficient for lot size, and then sort of just generally answer, what does it mean when a regression sum of squares is large relative to the total sum of squares? So what we want to do is go ahead and start with that confidence interval. And you can see it's right here, right? The confidence intervals are all right there. So if I want to conduct a null hypothesis, I can use that confidence interval to do it. So I can say that I can use the 95% confidence interval for lot size is 4.65 and 6.17, which means we are 95% certain that the true value of beta falls within this, or lies within this confidence interval, this implies that we can reject the null hypothesis because the confidence interval does not contain 0. We can also look at the p-value for lot size. The p-value for lot size's coefficient is 0.00, which is less than the 5% 0.05 significance level, meaning we can reject the null hypothesis. So those are the two main ways that you can test that null hypothesis. You can also look at the standard error, which is 0.3879696, which is less than half the size of the coefficient. So that's good too. What that means when we test that null hypothesis is that we do believe that the beta has some real value, which means that our x has explanatory value. Because remember, if we go back here and look at our regression equation, whether there's a natural log or not, if our beta is 0, then x is going to have beta times x is going to be equal to 0. And that means that x isn't going to influence our y at all. And that would be bad. So that's why we test that null hypothesis. The next part is to interpret the coefficient for lot size. The coefficient for lot size is 5.4. We know what a lot size is. We know what a sale price is. Sale price is in dollars and cents. Lot size is in square feet. So I'm going to give you guys the sort of code here first, and then we'll do the specific version. So the code or the kind of background is a marginal change in x will tend to have a beta hat sized effect on y. And because this is a multiple regression, there are 4 variables, right? There's sale prices are y, and then we have x is lot size, bedroom, and bathroom. We want to hold those constant, holding number of whatever, let's say this, holding all other variables constant. Okay, so what does that mean for our understanding of the coefficient for lot size? Well, so we could say a marginal change in lot size, or we can get more specific, right? There's more than one way to say this. I just give you this sort of format. So more specifically, we can say each additional square foot of lot size will tend to increase, because it's positive, 5.4, the sale price of a house by $5.41, holding number of bedrooms and number of bathrooms constant, right? If I were to interpret the coefficient for bedrooms, I would say each additional bedroom tends to increase house sale price by $5,826.80, holding lot size and number of bathrooms constant. If I wanted to look at the coefficient for bathrooms, I would say each additional bathroom a home has is going to tend to increase the sale price of that home or that house by $19,750.21, holding number of bedrooms and lot size constant. What does it mean when the regression sum of squares is large relative to the total sum of squares? Remember, TSS is equal to RSS plus SSR. So That means that if we're looking at how our model works, remember that the total sum of squares is the measure of the variation between the real value of y and the mean for y. And then the regression sum of squares, or the model sum of squares, which is going to be right here, that is the sum, the sum of the estimated y's minus the mean squared. And then the sum of squared residuals is just the sum of residuals squared. And so what that means is the model is measuring the variation in those estimated y's, those y hats that come from our regression equation. The TSS, the total sum of squares, is the true variation in y, and those residuals, remember, are just yi minus y hat I equals ui. So if the total sum of squares and the regression sum of squares, or the model sum of squares, are relatively large or close together, they're going to be close together. If the RSS is large relative to the TSS, that means that the SSR is small. That means that if we go through and say, okay, TSS equals RSS plus SSR, the true variation in y is equal to the estimated variation in y, and then our residuals. The closer these two get together, the smaller the residuals are, and the better our model is at explaining the variation in y. It's going to give us a higher r squared, which again is our explicit measure of how much variation in y we have. And in this case, we have a total sum of squares that's 3.88. We have a model sum of squares that is 1.88, and a residual, or a sum of squared residuals, that's 1.99. So we can see that the residuals make up a little bit more than half of the explanatory power, and the model is a little bit less than half. And if you go over here and look at the r squared, you see that the r squared is 0.486, which says that our model tends to explain 48% of the variation in y. And we see that, right? If we were to divide the model sum of squares or the regression sum of squares by that total sum of squares, we'd get that r squared variable. So that's number 4. The last bit, I'm going to kind of just scooch this back up here. A regression equation that contains race, age, years of experience, years of education, and years of tenure with a company to explain variation in wages has which problem? And this is looking at talking about the problems we might encounter doing multiple regression analysis using multiple explanatory variables. It's not omitted variable bias, because remember, omitted variable bias means you're leaving something important out. We might see that there's something missing, but that's not what this question is really asking about. What this question is asking about is it's looking at the fact that we have a lot of variables that are saying very similar things. Age, years of experience, years of education, and years with the last years of tenure with a company are all measures that are going to be very similar. They're going to be very highly correlated, right? No one's going to be 5 years old and have 10 years of education, or 20 and have 1 year of and have 10 years of education and 0 years of experience. So we're going to see a multicollinearity problem there. And so that's something that you want to look out for. And again, remember, multicollinearity is just too many variables too closely correlated trying to kind of explain the same thing. Last question, qualitative data. Qualitative data is not impossible to use. We would just have to code it. So A is incorrect. It is often categorical. It is not numerical. That would be quantitative data. And it is used in economic analysis. So our answer is B. So 2 B's in a row. There we go. That's it. So Hopefully that helps. Hopefully that's a nice review of some of the big ideas we've talked about so far. Let me know what questions you have. Hit up the discussion thread. I've answered a lot of the questions in the discussion thread already. Let me know, and I will see you next time. Have a beautiful day. Take care, everybody.